welcome back for our second to last section of the semester, in this chapter anyway. So the first section was inverse functions of this chapter. How do we find what they are? The final two sections are going to study another major function in algebra and its inverse in the final section that we're going to see. So what we're studying here are exponential functions. And what I'm going to do first is just a little comparison. The first sheet of notes there to jot down, first board. We're used to seeing equations and functions that look like this. This is called an algebraic function. The key thing here is that my independent variable, or my input variable here, is my base of the exponent. So this x is being squared, I can see. The power of the exponent is a constant, so that isn't the part that changes. What changes is the the numbers that I pick to fill in for the base. An exponential function behaves in the opposite manner. So what you can see here is that my independent variable, or my input, is now actually the exponent, or the power, with this base, so this is now staying constant. Maybe this is 3 to the power of x. So when I pick numbers to input, I plug them in for the exponent. Other key things with exponentials, we talk about bases greater than 0, so positive bases, with base not equal to 1. The reason for that is if I were to raise 1 to any power, my answer is still just 1, multiplying it over any number of times. So to do one here quickly on the left board by hand and by using a table, we're going to see how this function behaves. What I'm going to do first is just simply pick three numbers. Let's get a sense of where these points are. Okay? So first of all, if I plug 0 in for x, think about what I'm doing here. I'm just taking my input, it's the exponent, and I'm doing 2 to that power. Now, hopefully you remember, so a couple exponent properties that are going to be important here are, first one being 0 property. Any base raised to a power of 0 always has a value of 1. So there's my first point on this function. Secondly, if I plug 1 in, 2 to the first power is equal to, just think it's 2 itself. So there would be another point on my function. Secondly, if I plug 2 in, 2 squared is equal to 4. Okay. Another one that I want to make sure we're clear on too, just so we can get a sense of what these functions do. What happens if I plug a negative value in for our input? Do 2 to the negative 3 power. Now, hopefully remember again properties of exponents. A negative exponent does not change the value of its base in any way. What it does is it is the reciprocal fraction of that term with a positive exponent. So what I have to think is 2 to the negative 3 flips to 1 over 2 to the positive 3. And then I just do 2 to the third, which is 8. So if you can think of it with another particular example, 2 to the third would be 8. Therefore, 2 to the negative third would be 1 over 8. Now what I'd like to do, and I'm not even going to sketch the function here yet, but if I even just plot these 4 points, first one is 0, 1. Second one is 1, 2. Next one is 2, 4. So you can see these points are going to grow at a rapid rate. Negative 3, 1/8 would be about here. Okay, so you can see this curve happening. Not even going to sketch it yet. I'm going to show you what that is on the next characteristics, but a really important thing that's going to happen here is that the parent of an exponential function is never going to hit the x-axis. That'll be important here. But next thing to jot down are these characteristics of a new parent function that we're dealing with. So with that example there, that's really going to be the last time that I ask you to find specific points on these graphs. More importantly, you need to know what the parent graphs look like. So as I've always stressed, I never care too much about particulars other than things like intercepts, vertex of parabolas, but what I do care very much about is that you know the general shapes of things. So some important characteristics of exponential functions. I'm going to come up with a list of 6 here. One is that we have a horizontal asymptote at y equals 0. Okay, new word here. Horizontal asymptote. What is this? So it is a line. Y equals 0 is a line. It is a line. You can kind of think I'll kind of call it imaginary in a way. That is not an actual part of the graph. That an exponential function will approach but not cross. Okay. It'll make a lot more sense when I put a visual up there. But a horizontal asymptote at y equals 0, that is the x-axis for the parent function anyway. So there's going to be kind of this imaginary dotted line that I'm going to sketch on the board eventually that will act as a guideline. It'll act as a line that the function will approach, but it will not actually cross. Secondly, exponential functions have no x-intercepts. Okay. Or at least the parent graph of them will not have an x-intercept. Okay, we will have some that do cross the x-axis, but parent functions of exponentials do not have x-intercepts, and it's because of this. This line at the x-axis, it will not actually cross, it just approaches it. Third characteristic, the parent function has a y-intercept at 0, 1. And this will be true for anyone. Look at the first point we found in our last example. It is the y-intercept because I plugged in 0 for x. Fourth, the domain of an exponential is always all real numbers or negative to positive infinity. The range is always 0 to infinity, or y greater than 0. Okay. And finally, they are continuous, just like polynomials. Okay, so again, a list of characteristics that's going to be true for all of these parent graphs of exponential functions. What do they look like then? So here's that general shape that you're going to have to keep in mind throughout this section. First one, if A, meaning the base, is a number that is greater than 1. So 1, 1.5, 2, 6, 10, whatever. If the base is a number greater than 1, here's what the exponential graph will look like. First of all, just to give you a reference of what those characteristics were, this is how I'm going to denote that horizontal asymptote, just kind of with a dashed line, y equals 0. So the graph will never hit this, but it will approach it in one direction. The graph always has a y-intercept at 0, 1, and then what it does is the graph increases as you go left to right, and then gets closer and closer to that x-axis, or the horizontal asymptote, without ever actually crossing it. So again, it kind of goes in this swoop here. It rapidly grows as you go left to right. Okay, we have one other similar case. If A base is between 0 and 1. So think of like a fraction between, like a half, or 3/4, or 1/3. So if it's a fraction that is less than 1, what the graph will do then, once again, it's going to have the same horizontal asymptote. So again, horizontal asymptote, kind of an imaginary line, guideline that it will not cross. Once again, y-intercept of 0, 1. But here's what it's going to do. This picture is actually going to flip. So it's going to start at positive infinity from the left side and now work its way down towards the x-axis, which once again it does not cross. So another way of describing that is it decreases left to right. And then the final characteristic and note that I would make here, once again, all of those characteristics apply to the parent graphs, but all previous translations and reflections still apply. I'll show you what that looks like in one of the final examples here. So again, that list will be something very important to keep side by side as you work through problems, along with these two general pictures of what these will look like. And again, all based on, do I have a base greater than 1? It'll increase to the right. And if I have a base that is less than 1, or a fraction, it's just going to decrease left to right. Again, that general picture is the one to keep in mind. So what we're going to finish with here, just a couple examples. And these are going to be quick, as I mentioned, because I'm not going to require that you use a table to find points necessarily. You always can if you want to, depending on how specific you want to make it. First, we're going to graph y is equal to 3 to the x. Okay. So what I just think of is I think of my characteristics, right? This is very similar to, this is one of our parent graphs actually, and it fits into the template for number 1 because I have a base that is higher than 1. It's 3. So what that means is even before I find any points or any other characteristics, I know it's going to have that general shape. Okay? So let's think. I know that I have a y-intercept at 0, 1. Okay? And the reason for that is anytime I have an exponent of 0, that base to a power of 0 is always 1. Next part. These are going to be the key things that I want you to use for these graphs. First off, label what I like to call your anchor point that I know I've used in other sections. Number 2, also label the horizontal asymptote. Okay. Now, this one, once again, it's going to be just like a parent function. So the horizontal asymptote, if I go to my graph here, it's just going to be the x-axis. So the way, I'll just label it like this, HA, horizontal asymptote, at y equals 0. Okay, so this is what I would like to see. I would like to see the horizontal asymptote labeled, and I would like to see the anchor point labeled, which is going to be that y-intercept. Okay? But it may not be if we have different translations involved. So to finish off this graph, all I want you to keep in mind is what's the general shape. Does it run uphill to the right? Does it run downhill to the right? And this one, because of what the base is, this one is going to run uphill to the right, and once again, as you go to the side, it is going to approach that horizontal asymptote but never hit it or go below it. reason being, as we said before, the domain is all real numbers because I can increase side to side as much as I want to. The whole x-axis would be covered up. But I am never going below the x-axis, which means that 0 nor any negative y value is ever being used in these questions. Okay, so that's the first one. That's what a parent graph would look like. Let us now take a look at some of these translations and involve those. So the next one we're going to do is y is equal to 2 to the x minus 3. So y is equal to 2 to the x minus 3. Okay, now this one I'm going to visualize before I write any information down. Review from previous sections. Minus 3 at the end shifts the whole graph down 3 units. Okay. Number at the end shifts it up or down, vertical shift. So what I'm going to do here, I always want to start about thinking about the anchor point. If I have a point at 0, 1 on the parent graph of a function, what this means I have to do is I start here. Translate that point down 3 units. So from here I go down 1, 2, 3, which lands me at the point 0, negative 2. Translated 3 units down from 0, 1. Next part. So what I'll do then, I'll use that as my anchor point. Okay. Next, my horizontal asymptote also shifts down 3 units. So think of it this way. If I normally have a horizontal asymptote as the x-axis, I now go down 1, 2, 3 units and make a horizontal line here. Okay, so horizontal asymptote here, and what you can see, I just said I went down 3 units, so that is a horizontal asymptote at y equals negative 3, the equation of that horizontal line. So again, everything from a parent graph just got translated down 3 units. I now sketch the graph. There we go. Same general shape. Kind of flattens out toward the asymptote. Increases as we go up to the right there. Okay. Final one that we're going to do here. We're going to involve one that has both a reflection along with a horizontal shift. All right, so this one we're going to do, actually we'll involve all 3. Y is equal to negative 2 to the x plus 1 plus 4. So y is equal to negative 2 to the x plus 1 plus 4. Let's get our transformations written down off to the side. This one has 3. First of all, the negative out in front of an entire function flips over the x-axis. So I've left this up here for a reason. When I graph, this picture is now going to be kind of flipped. This has a reflection over the x-axis. And once again, if you forget these, make sure you go back to chapter 2 to review what all of these translations are. Next, a number next to x, remember, shifts horizontally. Always remember, though, it's always the opposite sign of what's here. So it shifts 1 unit left. So remember, opposite of what you would expect. The plus 1 means I actually go left 1. And then the plus 4 at the end means I shift 4 units we're at the end, vertical shift. Once again, let's now come up with our key characteristics. Once again, always start your thinking with that anchor point that is normally at 0, 1, and now just let it undergo the transformations that we have. If I would normally start at 0, 1, I have to shift that point 1 unit to the left though. So I'm going to go -1 in the x direction. But I must also shift that point 4 units up in the vertical direction. So instead of 0, 1, I'm now taking that point left 1 and then up 4 units. So here's my new anchor. It's -1, 5. Okay, and again, those are just the coordinates of the point after undergoing these shifts. Finally, as I mentioned before, we now do the same thing with the horizontal asymptote. And once again, this is always going to directly correspond to the vertical shift, okay? So I'll make a note of that actually here at the bottom. The horizontal asymptote will always correspond to a vertical shift. So if we translated the graph up 4 units, that means I'm going to start at the x-axis and shift that up to y equals 4. And you can also always pair in your mind that asymptote is always going to be 1 unit below the anchor point. So horizontal asymptote at y equals 4, sorry, not showing up very well there. Horizontal asymptote at y equals 4, we can now do the quick and easy sketch. Once again, up to the right, oh, I'm sorry, we'll not do that. We're going to amend this example a little bit because I screwed it up. My apologies. Pretend that one did not have an x-axis reflection there. That would actually change points around from what they were. So my apologies for this one in particular. Get rid of the transformation that reflects it. That would still apply. Anytime we have a negative out in front of a whole function like that, it would flip it downward. However, it would have thrown off other information that I didn't account for here. So once again, recap, my apologies. Do this one without the without the reflection, so it'll have the same general shape compared to what we've had. But once again, shifting the anchor point according to the other shifts